depending on the context. Now, for the next one, let's talk about error handling. When we think about error handling in C, you're probably thinking of something like this. You have a function that takes some arguments and an out parameter and returns an error code. Now, how you're supposed to use this is that you declare some error code variable, and then every time you do a task, you get the error from the return slot, and then you check for it, and then you do this again and again. And now some people thought, well, this is quite repetitive. I don't want to repeat myself. So they decided to use goto. And they just have a label at the end of the function. And, this approach can sometimes work. But if you know anything about goto, you might know that it's kind of problematic. There are some issues that can appear with it, some security issues, maybe in some very popular software that is used by millions of people around the world. So what could we do here to do better? What can we do in modern C? Well, I have here an example where I have a function that reads some file and returns the contents of the file. And the struct that it returns has a pointer to the data that we read from the file, the size, which is the length of the data that we read from the file in bytes, and then this valid member, which for all intents and purposes, it's like a Boolean. And what we're doing here is that once we read the file, all we do is that we check if it's valid. And when it comes to the actual error, say the file was not found or the file was whatever happened, the cosmic ray hit your hard drive and something really bad happened, those are usually handled in a centralized manner. So you would have something like a logging system for errors that would report these errors up. But in our context at the call site, all we know is, was I successful or was I not successful? Is the data that I got back valid or not? And this is the case because often this is what actually happens in real code. We don't have enough information at every single call site in order to handle an entire enum of errors. And not just this, but this pattern with valid here can compose very nicely. So let's look at a more complex example. Here I am loading a file. Then I am loading an image from that file, so sort of decompressing that image into an array of bytes. And then I am loading that as a texture. I'm uploading that as a texture on the GPU. And at the end, I only check if texture is valid. And the way this works is that if there was a failure at any point in this code, so say the file contents were not loaded or the image was not decompressed correctly, then that certain struct will be invalid. And then when I pass it to the next function, it will check whether the data that it's working with is valid or not. And if it's not, then it will simply return it. And this is quite similar to stud optional from C++. And there are actually proposals for C++ that were trying to achieve a very similar thing. So in this proposal from Simon Brand about monadic interfaces for stud optional, the idea is that you can get an image and then you can do a bunch of operations as long as whatever the return type is still valid. It's still there. The optional is true. And at the end, you just return it. And if at any point it fails, then the optional will just be false. And this is essentially what we're doing here in modern C as well. The big difference would be that we are packing this into the design of our data structure instead of having it be generic like stud optional. But at the same time, we don't have to do that meta chaining. We can just call our functions as normal, and it works very nice in the debugger, which is very nice. And as you'll notice here, we're working just with values. We're not working with a lot of pointers, which is really a good sign in modern C. And at the very end, we just, whenever we need to see the final result and do something with it, we can just check if it's valid. Now, it is also valid if you want to go with the route where you have an error code inside of your struct instead of the valid Boolean. That is a perfectly good approach. And in fact, it has parallels in other languages and in C++. In C++, for example, maybe you have heard of this proposal called std_expected, which is quite old. It was first introduced by Andrei Alexandrescu all the way back in 2012. And the idea here is that it's kind of like std optional, but instead of a Boolean flag, true or false is the variable there or not, we have an error code. So we can actually handle more specific errors that have occurred. And new programming languages such as Rust actually have this as the built-in error handling module. In Rust, for example, you do not have exceptions. Instead, you have the equivalent of std_expected, which is called result in Rust. And you can see in this code, what happens here is that we are opening a file, and then we are essentially using pattern matching to check, hey, did I have an error? Where in that case, propagate the error. And otherwise, then great, I have a file. Let me do stuff with it, like read from it. And another language called Zig takes this even a bit further. In Zig, this mechanism is actually built into the language instead of being a library feature. So you'll notice in the first function, there's the exclamation mark right next to void. And what that represents is that, hey, this function can return an error. And then on our, we are parsing unsigned 64 integer, and then we're catching an error and handling it directly in the language. And on this other function, what we're doing, this other variant of our do a thing function, what we're doing is that we're using the try keyword, which in Zig basically means catch the error, and if there was an error, then return the error, propagate it. And this is a very interesting mechanism. What this essentially achieves is something very similar to exceptions, except the flow of how the exceptions propagate is explicit. And the second important factor is that there are no heap allocations. Exceptions in C++ do heap allocations, but here the exceptions are the errors are simply returned as values. And what's interesting is at ACCU in 2019, Herb Sutter gave a very interesting talk where he essentially presented a similar kind of mechanism, very, very similar to Zig's, but for C++. And I think this sort of shows that there is a lot of thought put in this, there's a lot of developments in this space of systems programming languages. And C++ is now evolving alongside many other languages. It is not the sole systems programming language where the whole discussion happens. Now, let's talk about generic